Oh, right, so we're going to look at mass spectrometry now and how we can use this in organic chemistry. Now, you would have done a lot about this in the first part of the course in the first unit that you did, and looked at the uses and how it works. So I just want to do a quick overview so we can have an understanding of how we can use this for organic chemistry. So, let's have a look at how it goes. First of all, we inject the sample. Remember, the whole of the mass spectrometer is in a vacuum. So these are really harsh conditions. So I inject my sample, it gets vaporized first of all. So all the organic molecules are vaporized all on their own. I then fire an electron at it. So if I've got some molecule M, I fire an electron at it. That gives me M plus, and obviously an electron. So if you think about it, I'm the molecule. I get fired an electron at me, like so, and that kicks out one of my other electrons, like so. So the electron that gets fired at me goes through, and then at the same time it takes out one of my electrons. So I'm now positively charged. I then get accelerated through the mass spectrum, and then I go through the magnetic field here, and then I finally get detected at the bottom there. So these are really harsh conditions for organic molecules. So, well, for anything really, I don't think you'd want to do. So we're going to look at how we can use this. So remember, it's not just a little bit, a walk in the park for the molecules. This is serious stuff to have this done to you. If you're an organic molecule, have an electron fired at you first of all, that knocks one of your electrons out. You're now a positively charged ion. You then get accelerated through an electric field, pushed through the machine, through a magnetic field, deflected, and then you finally get detected. Are many organic molecules going to be able to stand up to that? Probably not. So let's have a look at that in a bit more detail. Okay, so we're going to look at what happens with ethanol. So ethanol mass spectrum gets put in the machine, gets a positively charged, and this is the mass spectrum that I expect to see. Y-axis is relative abundance, and M over Z value, that's a mass to charge. We assume that everything's got a charge of just 1 plus. You've got to identify the ions. So the first one you always look at a mass spectrum is the one furthest to the right hand side. So it's going to be this boy here. So look, what is that? So that's 41, 2, 3, 4, 5, 6. That has an M over Z value of 46. Now, if you add up all the relative atomic masses of your atoms here, ethanol has a molar mass of 46. So that peak there is your molecular ion. That is the whole molecule with a plus charge. So if you had to identify what that 46 is as the ion, it would be CH3, CH2, OH plus. It's really important. If they want you to identify the ion, you put the plus charge on there as well. So that is going to be 46. But you can see I've got other peaks going on here. So what's going on? Well, let's have a think about it. You've got ethanol, he's got a plus charge on it, he's in a vacuum, he's going to be in a very excited state. What's going to happen? He's going to go crazy, and what happens is bonds start breaking and you get fragmentation patterns going on. So not all the molecules survive. Some of them break up in the mass spectrum. So they fly through the machine, and as they do, bits fly off here and there all over the place. And we can use this to build up what the molecule would look like. So if you think about this as a person, so think about it as me. So I get put through the mass spectrum like so. I'm not going to be very happy, but I've got a plus charge on me. So as I fly through, remember there's millions of me doing this, a bit scary. So as I'm going through the machine, bits are going to start falling off of me. And we can use that to build up molecules. So what am I likely to do? Well, most likely an arm's going to fall off. So I'm going to see the mass of one arm. Probably my head would fly off, so I see the mass of a head. Maybe a leg would fly off, so I see the mass of a leg. Things like that. So I'd be able to see, I say, oh, okay, well, I was made up of an arm, a head, a torso, and a leg, and so on. What you wouldn't see, and this is really important, is the mass of 2 arms. So you're not going to see here on my mass spectrum 2 arms, because if one arm flies off and one arm flies off, the arms aren't attached together in any way. Equally, my legs, if one leg flies off, the other leg flies off, they're not going to, I wouldn't see the mass of 2 legs in the mass spectrum. Equally, I wouldn't see 2 heads. That'd be scary. So you'd only ever see 1 coming through. So what you can do is you'd be able to say, well, when you're building me up again from your pattern, you'd be able to say, well, he's got 2 arms, but they weren't joined together in any way. They weren't like joined like that. They were separate, on separate bits of him, and so on. So we can use that to build up the pattern for ethanol. So what do I see? Well, I see a peak at 45. What do you reckon that's been? Look at this molecule. Well, what's likely? I've lost 1. What's it going to be? It's going to be a hydrogen, isn't it? You haven't got anything else that has a mass of 1. It's likely to be that boy there. So that peak there is going to be CH3, CH2O plus for that one. What else do I have? I have a peak going on at 31. That could be, so I kind of try and look at this as the difference. I started off at 46 and I've now got a peak at 31. 46 minus 31 is 15. What adds to 15? Well, a methyl group, CH3, adds up to 15. So that's probably that methyl group knocked off there. So that peak is likely to be CH2OH plus, like so. What else have I got? I've got 29 here. 29 is actually a methyl group and a CH2 group. So that's CH3, CH2 plus 15 plus 14 to give me 29. I've also got something knocking in here. This is 11, 12, 13, 14. That's at 15 there. What do you reckon that's going to be? Well, that's going to be the methyl group, isn't it, at 15? So that's going to be CH3 plus, like so. And I've also got 27, which is likely to be C2. So that's going to be, C2 is going to be 14. No, it's not. C2 is going to be 24, 25, 26, 27. CH2, CH3. So it looks like I've lost an H2 there as well, which is quite likely to happen in a mass spectrum. Now, the main thing is when you tackle one of these exams, don't try to identify all of them, because if it's a complex organic molecule, you'd be there all day identifying fragments. You know, normally you have to identify a couple. The main one is that boy there. You've got to get that. That's giving you your molar mass, so you've got to be able to get that one sorted. The other ones, normally you're losing methyl groups, AS, you're losing OH group, things like that, and it just gives you but you can see, hopefully, how with infrared spectroscopy combined with this can tell us a lot about what our organic molecule actually made up of, the functional groups, and how they will then fit together. We're going to look now at high resolution mass spectrometry. Now, most mass spectrums, we get it to the nearest whole number, the M over Z to the nearest whole number, and that's fine for, you know, most of what we need. However, some mass spectra could give the M over Z value to 3 or 4 decimal places. Exciting. Okay, so you may think, well, what's the point? What's the point of that? Well, let's say I've got a parent ion of a mass of 200. It could either be C10H16O4, C11H4O4, or C11H20O3. All of those add up to 200. So what I could do is then put my sample through a high resolution mass spectrometry. And what that will work on is we can measure these to far better degree of accuracy. So rather than just taking oxygen, the isotope of oxygen as being 16, it's actually 15.99491. Hydrogen, 1, is actually 1.007829. Carbon 12, of course, by definition, is exactly 12. Okay. And what you could do, if you now use these numbers to add this up, so if we assume this boy is made up of carbon 12, hydrogen 1, and oxygen 16, that would have a mass of 200.1049, and so on. They all have, so although to the nearest whole number they're all 200, if I go to a high degree of accuracy, you can see they're different. So in a high resolution mass spectrometer, I would be able to tell the difference between these three formulas. So it can really nail it for us as exactly what it is, what atoms are actually in the organic molecule.